Welcome to Foundation Mathematics, sketching, interpreting, and solving using exponentials and logarithms. The objectives for this session are to sketch graphs of the form y equals a to the x and y equals e to the x and transformations of these graphs. We are also going to use and interpret models which use exponential functions, recognize how exponents and logarithms are related, apply the laws of logarithms, solve equations of the form a to the x equals b, and describe and use the natural logarithm function. Exponential functions are functions of the form f of x equals a to the power x, where a is a constant. Note that 3 to the power 0 equals 1, and, for example, 3 to the minus 2 equals 1 over 3 squared, which of course equals 1 over 9. Let's now take a look at some notation. This is x to the power y. X is the base, and y is the index, power, or exponent. Now let's take a look at an example. The values of y equals 3 to the power x are given in the following table. A graphical presentation of this is going to be shown here. So this is a point where x equals minus 3 and y equals 3 to the minus 3. Here, x equals minus 2 and y equals 3 to the power minus 2. Here, x equals minus 1 and y equals 3 to the power minus 1. Here, x equals 0 and y equals 3 to the power 0, which is of course equal to 1. When x equals 1, y equals 3 to the power 1. When x equals 2, y equals 3 to the power 2. When x equals 3, y equals 3 to the power 3. And so on. We can join these points to give us the graph shown on your screen. Notice that as x tends to infinity, 3 to the power x also tends to infinity. And as x tends to minus infinity, 3 to the power x tends to 0. The y-axis, or the line x equals 0, is an asymptote. Let's now take a look at another example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve example 2a first. We are required to sketch the graphs of y equals 5 to the power x, y equals 3 to the power x, and y equals 2 to the power x on the same graph. So let's do this. Here's y equals 5 to the power x. And here's y equals 3 to the power x. And here is y equals 2 to the power x. Notice that 5 to the power 0 equals 3 to the power 0 equals 2 to the power 0 equals 1. And also, notice that when x is greater than 0, 5 to the power x is greater than 3 to the power x, and that is greater than 2 to the power x. And on the other side, when x is less than 0, 5 to the power x is less than 3 to the power x is less than 2 to the power x. And when a is greater than 1, f of x equals a to the power x is an increasing function. For a greater than 1, as x tends to infinity, a to the power x also tends to infinity. And for a greater than 1, as x tends to minus infinity, a to the power x tends to 0. Now let's have a go at part B. We are required to sketch the graphs of y equals 1 over 3 to the power x and y equals 3 to the power x on another set of axes. So let's solve this. Here's the graph of y equals 1 over 3 to the power x. Notice that when 0 is less than a is less than 1, f of x equals a to the power x is a decreasing function. And as x tends to infinity, a to the power x tends to 0. Also, as x tends to minus infinity, a to the power x tends to infinity. And here's the graph of y equals 3 to the power x. The graph of y equals a third to the power x is a reflection in the y-axis of the graph y equals 3 to the power x. Now let's have a go at another example. We are required to sketch the graph of y equals a third to the power x minus 2 and give the coordinates of the point where the graph crosses the y-axis. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve this. We're going to sketch the graphs of y equals a third to the power x and y equals a third to the power x minus 2 and see how the two relate to each other. So here's y equals a third to the power x, and here's y equals a third to the power x minus 2. When x equals 0, y equals a third to the power minus 2, which equals 3 squared, which equals 9. For the first graph, when x equals 0, y was equal to 1. However, the corresponding point for x equals 0 is here. This is a translation of 2, 0. In fact, the graph y equals a third to the power x minus 2 is a translation of 2, 0 of the graph of y equals a third to the power x. We're now going to look at a very special exponential function. In exponential functions of the form f of x equals a to the power x, there is a value n which has a special property. At any point on the curve, the gradient of n to the power x is equal to the value of n to the power x. This particular value is represented by e. So in this graph, we have y equals e to the power x, and again, it cuts the y-axis at the point 0, 1. This is called the exponential function, e or exp. It is of the form f of x equals e to the power x, where e is a constant whose value is approximately 2.71828. Here it's given to 5 decimal places. There is a formula which relates to this function. Suppose first that x is a rational number. Then we have e to the power x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus, and so on, where 2 factorial equals 2 times 1, 3 factorial equals 3 times 2 times 1, 4 factorial equals 4 times 3 times 2 times 1, and so on. This is in fact a remarkable formula and merits some explanation. The right-hand side is supposed to be a sum that carries on in this pattern forever. Whatever value x we choose, the terms on the right-hand side gradually become smaller. Eventually, we'll be adding such small numbers that the value we have is equal to the value of e to the power x, up to our chosen level of accuracy. The exclamation marks are called factorials, and they mean that we are required to multiply all the numbers up to this number. Let's see how the value e relates to real-life questions. We begin by looking at exponential growth and decay. The exponential function e to the power x can be used to model real-life situations where the rate of increase is proportional, for example, to population size at a given time. Here's a sketch of exponential growth, y equals a times e to the power kt, where k is greater than 0. A is the initial value at time t equals 0, as shown here. We begin with a slow increase and then a rapid increase. Likewise, the exponential function e to the minus x can be used to model the rate of decay. Here's a sketch of the graph of y equals a times e to the minus kt, where k is greater than 0. This denotes exponential decay. The initial value is at a at t equals 0. We begin with rapid decrease and then a slow decrease. Do note that k is greater than 0, so plus or minus shows growth and decay respectively. A is the starting value at t equals 0, and t is used for time. So to summarize, exponential growth is modeled by y equals a times e to the power kt, and exponential decay is modeled by y equals a times e to the minus kt for constants a and k greater than 0 and variable time t greater than or equal to 0. We're now going to take a look at an example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's take a look at part A first. The following formula models the population of a village. P equals 12 plus 7 times e to the power t over 25, where P is the population in thousands and t is the time in years after the year 2020. We are required to calculate the size of the population in 2020. So let's solve this. In 2020, time t equals 0. And therefore, if we plug t equals 0 into the formula for P, we obtain P is equal to 12 plus 7 times e to the power 0. Here we've input t equal to 0. And tidying up gives us that P is equal to 19. And therefore the population is 19,000 in 2020. And now for part B. We are required to use the same model to predict the population in 2045. So let's solve this. Since t equals 0 in the year 2020, we have that t equals 25 in the year 2045. So, plugging in t equals 25 into the formula for P gives us P equals 12 plus 7 times e to the power 25 over 25. Here we've input t equal to 25. And this gives us 12 plus 7 times e to the power 1, which is equal to 31.028 to 3 decimal places. Therefore, the population is 31,208 in 2045. And now for part C. We are required to sketch the graph of P against T from 2020 to 2070. So let's solve this. In 2020, T equals 0 and P equals 19. Therefore, the graph of P equals 12 plus 7 times e to the power t over 25 will look something like this. And now for part D. We are required to explain whether we think this model would be valid when predicting the population in the year 3000. So let's solve this. In the year 3000, we have that T is equal to 3000 minus 2020, which is equal to 80. And therefore P equals 12 plus 7 times e to the power 80 over 25. We have input t equal to 80 into our equation for P. And calculating this gives us 301.390. This implies that the population is 301,390 in the year 3000. However, the model is not going to be necessarily valid for predictions that far into the future because we do not know if the current trends will continue. We are now going to explore inverses of exponential functions. The inverses of exponential functions are called logarithms. So the exponential relationship where a does not equal 1, a to the power x equals n, can be written in terms of a logarithm, or log of n base a equals x. Pause the video and have a go at this example. Press play when you're ready to view the solution. Let's take a look at part A first. We are required to write 5 to the power 4 equals 625 as a logarithm. So let's solve this. We have that 5 to the power 4 equals 625, and we've color-coded the digits in order to help us connect this to our theory. This can therefore be written as log 625 base 5 equals 4. Referring to the colors, you'll be able to see that a equals 5, n equals 625, and x equals 4. And now for part B, we are required to write 3 to the minus 4 equals 1 over 81 as a logarithm. So let's solve this. Again, we've color-coded so that we can connect the example to the theory. As you can see, 3 to the minus 4 equals 1 over 81, and therefore we can rewrite this as log 1 over 81 base 3 equals minus 4. Here we have a equals 3, n equals 1 over 81, and x equals minus 4. And now for part C. We are required to write 10 to the 9 equals 1 billion as a logarithm. So let's solve this. Again, we've color-coded this equation to give us that log of 1 billion to the base 10 equals 9. Here we have a equals 10, n equals a billion, and x equals 9. Now let's have a go at another example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's take a look at part A first. We are required to rewrite log 243 base 3 equals 5 using a power. So let's solve this. If we color code again, as shown here, then we can see that 3 to the power 5 equals 243, using the theory on the left-hand side of the screen. Here we have a equals 3, x equals 5, and n equals 243. And now for part B. We are required to rewrite log 625 base 5 equals 4 as a power. So let's solve this. Here again we can see that a equals 5, n equals 625, and x equals 4. So we can rewrite this as 5 to the power 4 equals 625. Now let's have a go at another example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's take a look at part A. We are required to find the value of log 25 base 5 without using a calculator. So let's solve this. We can let log 25 base 5 equal n, and then we can rewrite this as 5 to the power n equals 25. Clearly, the only value which is going to satisfy this is n equals 2. Now let's take a look at part B. We are required to find the value of log 27 base 3. So let's solve this. If we let log 27 base 3 equal n, then we can rewrite this as 3 to the power n equals 27. The only value of n which is going to satisfy this is n equals 3. And now for part C, we are required to find the value of log 8 base a half. So let's solve this. Again, write this as equal to n. And as you can see from the color codes, we can write this using the formula for logs as a half to the power n equals 8. And therefore, n is equal to minus 3. Now let's take a look at part D. We are required to find the value of log 8 to the power 7 base a. So let's solve this. If we let log 8 to the power 7 base a equal n, then we can rewrite this as a to the power n equals a to the power 7. And therefore clearly we have that n equals 7. We can also find logs on a calculator. Some calculators have specific buttons to find logarithms, such as the one you can see on your screen now. Logarithms to base 10 are denoted simply as log, and logarithms to base e are denoted as ln, and they are also known as natural logarithms. Now have a go at this example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's take a look at part A first. We are required to find the value of log 35 base 4 to 3 decimal places by using a calculator. So let's solve this. If you have the appropriate button on your calculator, you should obtain 2.565. You can check this by checking that 4 to the power 2.565 is approximately equal to 35. Hopefully these color codes will help you. And now for part B. Find log 23 base e to 3 decimal places by using a calculator. Let's solve this. Using a calculator, you can simply reduce this to ln 23, which will give you 3.135. And you can check that this is true by trying e to the power 3.135, and it should give you approximately the value 23. Again, we've color-coded to help you understand this idea. And now for part C. Find log 88 base 10 using a calculator. Let's solve this. Using a calculator, you can simply type in log 88. This should give you 1.944, and then you can check that 10 to the power 1.944 is indeed approximately equal to 88. Here's the color coding to help guide you through the process. Let's derive some results from these relationships. If a is greater than 0, then x equals 1 implies a to the power 1 equals n, and therefore n equals a, and in particular log a base a equals 1. If x equals 0, then a to the power 0 equals n. Therefore, n is equal to 1. And in particular, log of 1 base a equals 0. If x equals minus 1, then a to the minus 1 equals n. Therefore, n is equal to 1 over a, and in particular, log of a to the minus 1 base a equals minus 1. Let's now look at the multiplication law. Log m base a plus log n base a equals log mn base a. The division law. Log m base a minus log n base a equals log m over n base a. The power law. Log n to the power k base a equals k log n base a. Let's prove the multiplication law. Let x equal log m base a and y equal log n base a. Then we have, if we rearrange, a to the power x equals m and a to the power y equals n. Therefore, m times n is a to the power x times a to the power y, which equals a to the power x plus y. Therefore, x plus y equals log mn base a. However, we know that x is log m base a and y is log n base a. Therefore, we have that log m base a plus log n base a equals log mn base a. Now let's prove the division law. Let x equal log m base a and y equal log n base a. Then a to the power x equals m and a to the power y equals n. And therefore, m over n equals a to the power x over a to the power y, which equals a to the power x minus y. And therefore, x minus y equals log m over n base a. But we know that x equals log m base a and y equals log n base a. And therefore, log m base a minus log n base a equals log m over n base a. Now let's prove the power law. Let x equal log n base a. Then a to the power x equals n. And therefore, raising this to the power k, we have a to the x to the k equals n to the power k. And therefore, a to the power xk equals n to the power k. And so, log n to the power k base a equals x times k. We bring k to the front, and x is of course log n base a. And hence we've proved the power law. Here's a summary of the results. We can derive some more results from the power law. In the power law, let k equal minus 1. To give log x to the minus 1 base a equals minus log x base a. Let's have a go at an example. Pause the video and have a go. Press play when you're ready to view the solutions. Let's take a look at part A first. We are required to write log 2 base 4 plus log 6 base 4 as a single logarithm. So let's solve this. We are going to begin by using the multiplication law, since we're using the same bases and we're adding. Log 2 base 4 plus log 6 base 4 equals log 2 times 6 base 4, which equals log 12 base 4. Now let's take a look at part B. We're required to write log 18 base 3 minus log 2 base 3 as a single logarithm. So let's solve this. We're going to use the division law. Log 18 base 3 minus log 2 base 3 is equal to log 18 over 2 base 3, which equals log 9 base 3. And now for part C. We are required to write 2 log 5 base 8 minus 4 log 3 base 8 as a single logarithm. Let's solve this. We're going to use the power law and the division law. First, let's apply the power law. So 2 log 5 base 8 becomes log 5 squared base 8. And 4 log 3 base 8 becomes log 3 to the power 4 base 8. And so applying the division law gives us log 5 squared over 3 to the power 4 base 3. Which equals log 25 over 81 base 3. And now for part D. We are required to write log 8 base 10 minus log a third base 10 as a single logarithm. Let's solve this. We are going to apply the division law as shown here. and then tidy up to give us log 24 base 10. Now let's have a go at another example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's take a look at part A first. We are required to write log p cubed q squared times r base a in terms of log p base a, log q base a and log r base a. So let's solve this. We're going to use the multiplication law as shown here, and then the power law here, here, and we don't actually need to here, it's just left as it is. And hence we have the expression in terms of log p base a, log q base a and log r base a. Now let's have a go at part B. We are required to write the expression in terms of log p, log q and log r. So let's solve this. First apply the division law as shown here. And then the power law to each term. And hence we've expressed our expression in terms of log p base a and log q base a as required. And now for part C. Again, we're going to apply the division law as shown here. And then apply the multiplication law to this term. And log r to the 5 is left as it is. And finally we apply the power law here, here and here. And hence we have our expression in the required format. And finally for part D. Let's solve this. Again, we apply the division law as shown here, and then apply the power law to the second term. So log q base a stays as it is, and log a cubed base a becomes 3 log a base a. However, we know that log a base a is equal to 1, so let's tidy up. Log q base a stays as it is, and 3 log a base a simply becomes 3. Now let's have a go at another example. Pause the video and have a go. Press play when you're ready to view the solutions. Let's solve this. We are required to solve log 4 base 12 plus 2 log x base 12 equals 2. Let's rearrange, firstly by applying the power law to the second term here, and then the multiplication law as shown here, and then re-express this log in terms of powers as shown, and then solve for x. So x squared is now 144 divided by 4, or x squared is 36. hence x equals 6. Now let's have a go at another example. Pause the video and have a go. Press play when you're ready to view the solution. Let's solve this. We are required to solve the equation log x plus 17 base 10 minus log x minus 1 base 10 equals 1. We're going to begin by applying the division law, as shown here, and tidying up, or rather re-expressing in terms of powers, then multiplying out, and expanding, and finally rearranging and solving gives us x equals 3. Let's now remind ourselves of some of the laws of logarithms: the multiplication law, the division law, the power law, and the other results or derivations. Using logarithms and your calculator, you can solve equations such as a to the power x equals b. Let's now take a look at an example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's take a look at part A first. We are required to solve 7 to the power x equals 89 and give our answer to 3 decimal places. So let's solve this. 7 to the power x equals 89 implies that log 89 base 7 equals x. As you can see from the colour code, a equals 7, x stays as it is, and n equals 89. Using the log button on your calculator will give you x equals 2.307, and you can check that this is correct by plugging 7 to the power 2.307 into your calculator, and it should give you approximately 89. And now for part B. We are required to solve 3 to the power 8x minus 3 equals 63 and give our answer to 3 decimal places. So let's solve this. 3 to the power 8x minus 3 equals 63 implies that log 63 base 3 equals 8x minus 3. We've plugged in from the colour code, you can see a equals 3, x has been substituted by 8x minus 3, and n equal to 63. Using the log button should give you that 8x minus 3 equals 3.771. And then we can check that this is correct by plugging in 3 to the power 3.771 into our calculator, which will give us approximately 63. So rearranging, we have that 8x equals 6.771. And therefore, x equals 6.771 divided by 8, which is equal to 0.846. Now let's have a go at another example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve this. We are required to solve 11 to the power 2x minus 5 times 11 to the power x plus 4 equals 0, giving our answer to 2 decimal places. We can rewrite this equation as y squared minus 5y plus 4 equals 0, where y is equal to 11 to the power x. Factorising gives us y minus 4 times y minus 1 equals 0. So either y equals 4 or y equals 1. If y equals 4, then 11 to the power x equals 4. Or colour coding will allow us to see that a equals 11, x in green is as it is, and n is equal to 4. And this allows us to convert to logs. So x equals log 4 base 11, which when plugged into your calculator gives x equals 0.58. If y equals 1, then we have that 11 to the power x equals 1, and therefore x is equal to 0. So this is our other solution. Now let's take a look at another example. We are required to find the solutions to 5 to the power x plus 3 equals 3 to the power x plus 1, giving our answer to 2 decimal places. Pause the video and have a go. Press play when you're ready to view the solution. So let's solve this. If we log both sides of this equation, we have log 5 to the power x plus 3 equals log 3 to the power x plus 1. And then, using the power law, gives x plus 3 times log 5 equals x plus 1 times log 3. And expanding gives us this equation here. And finally, rearranging and dividing by log 5 minus log 3 gives us that x is equal to minus 7.30. We can check that this is indeed the case by plugging back into the original equation. So if we plug x equals minus 7.30 in, we can see that 5 to the power minus 7.3 plus 3 equals 3 to the power minus 7.3 plus 1. Your calculator may be confined to only base 10 or base e, so in some of the previous calculations it is possible that you may not have been able to carry out the calculations on your calculator. If this is the case, then the next formula will be very useful for you. This is the change of base formula, which states log c base b equals log c base a divided by log b base a. Let's take a look at an example which will allow us to apply this change of base formula. Pause the video and have a go. Press play when you're ready to view the solution. So let's solve this. In this example, using the change of base formula with base 10, we are required to find the value of log 4 base 11 given our answer to 2 decimal places. Let's apply the change of base formula. So we have log 4 base 11 equals log 4 base 10 divided by log 11 base 10. A equals 10, C equals 4, and B equals 11. We can now plug in log 4 base 10 and log 11 base 10 into our calculator to give us this fraction. This is log 4 base 10 and this is log 11 base 10. The fraction is equal to 0.58 to 2 decimal places. We're now going to revisit natural logarithms, or logs to base e. Remember the exponential relationship, a to the power x equals n, can of course be written in terms of a logarithm, as log n base a equals x. Recall also that there exists a value e such that the gradient of e to the x is equal to the value of e to the x. We're going to let f of x equal e to the power x. And the function y equals ln x, which equals log x base e, is the inverse of y equals e to the power x. Let's now take a look at an example which will allow you to get used to this notation. Pause the video and have a go. Press play when you're ready to view the solution. Let's take a look at part A first. We are required to solve 2e to the power x equals 7 and give our answer in exact form. So let's solve this. We can rewrite this equation as e to the power x equals 7 over 2. We have, of course, simply divided through the equation by 2. And therefore, e to the power x equals 3.5. So if we take natural logs of both sides, so ln of e to the x equals ln 3.5. Now, since the natural log is the inverse of e, we have x equals the natural log of e to the power x. And therefore, x is equal to the natural log of 3.5. Now let's take a look at part B. We are required to solve ln of x equals 80. So let's solve this. When ln x equals 80, we have e to the power ln x equals e to the power 80. Since e is the inverse of ln, we have x equals e to the power ln x. And therefore, x equals e to the power 80. Now let's have a go at another example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's take a look at part A first. We are required to solve e to the power 5x plus 2 equals 8 and give our answer in exact form. Let's solve this. This equation, after taking natural logs, gives us ln of e to the power 5x plus 2 equals ln 8. Since ln is the inverse of e, we have that 5x plus 2 equals ln 8. And rearranging this gives us 5x equals ln 8 minus 2. And finally, dividing by 5 gives x equals 1 over 5 ln 8 minus 2. Now let's have a go at part B. We are required to solve 8 ln x plus 2 equals 9 and give our answer in exact form. So let's solve this. Now 8 ln x plus 2 equals 9 implies 8 ln x equals 7. We've simply subtracted 2 from both sides. If we divide the equation through by 8, we obtain ln x equals 7 over 8. And therefore, raising both sides to the power e gives us e to the power ln x equals e to the power 7 over 8. Since ln is the inverse of e, we have that x equals e to the power 7 over 8. Now let's take a look at part C. We are required to solve e to the power 2x minus 2e to the power x equals 15 and give our answer in exact form. So let's solve this. Rearranging this equation gives us e to the power 2x minus 2e to the power x minus 15 equals 0. As you can see, this is a quadratic in e to the power x. And so if we factorise, we obtain e to the power x minus 5 times e to the power x plus 3 equals 0. Therefore, either we have e to the power x equals 5 or e to the power x equals minus 3. However, we know that e to the power x is greater than 0, and therefore e to the power x equals 5. Finally, if we ln both sides, we have ln e to the power x equals ln 5. And so x is equal to ln of 5. This brings us to the end of this session. If you have understood its contents, you should be able to sketch the graphs of the form y equals a to the power x and y equals e to the power x and the transformations of these graphs. You should also be able to use and interpret models which use exponential functions, recognize how exponents and logarithms are related, apply the laws of logarithms, solve equations of the form a to the power x equals b, and describe and use the natural logarithm function. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.